Okay, now today's topic for chemistry is like we'll start with the developments which led to our modern concept of atomic structure, and that you too much agree is about quantum theory. Now it was not like a scientist dreamt about and later in the morning he started with giving us about quantum theory. There were certain developments between Bohr's atomic model and quantum theory, and these became the basis for Schrödinger and other scientists to conclude upon quantum theory. So what are these developments? We'll try to discuss them. Actually it's there in your books and all, but according to my experience, many students come to me, what is the importance? So basically today I just wanted to discuss the importance of their theories. So I will start developments leading to modern concept of atomic structure, or you can say quantum theory. Now in this basically we have two types of concepts. First one, if I start with, is your De-Broglie's wavelength. Now what is De-Broglie's wavelength? Now as you have already seen in the case of light, it was assumed that light is having only wave nature, but later on Planck gave his theories and told us that along with this wave nature, it has also got particle nature. Now just his basis of De-Broglie became that theory, and he said if light is going to have dual nature, why can't other particles also have dual nature? If they are moving, why can't they also have a dual nature? And he concluded that if supposing I assume a particle is moving in a straight line, it's going to be like the dual nature will also be shown by that particle. That means if it is not moving only in the form of a straight line, it will show some kind of wave also. And he went through various theories and all. Now those theories and those calculations luckily are not part of your syllabus, so we are not going to discuss it. Basically come back to the main points which are regarding our syllabus. So that is, he calculated certain calculations, and on this he gave us a formula that the wavelength of the moving particle can be given by a formula lambda is equal to h upon p. Now what is p over here? P stands for the momentum and h is for Planck's constant. And you know its value, we have already done in Planck's theory. Now p, you know it's momentum, so what can be the other way of writing p? So I can say, p is momentum and nothing but mass into velocity. So I can also say wavelength will be equal to h upon mv. This is one form of the theory given by De-Broglie. Now sometimes it happens to be like this lambda, instead of giving you wavelength, the examiner tries to confuse you by giving kinetic energy. And obviously in this case the m is what? Mass. So mass of what particle I am talking about? It's going to be for electrons. So m is the mass and v is the velocity of the particle, and m is the mass of the particle. Okay. Now the problem is, now you will not agree with me very directly that if I say particle is moving in a straight line, it's not, you will say yes it is moving in the straight line, there is no kind of wave made by the particle. But the logic for this is, see, if the mass is going to be too high, obviously the value for lambda will be very low, it's inversely proportional. So if you have a huge particle, obviously the lambda will become small. More the mass of the particle, lambda much more less. And or we can say in that ways that our eyes are not at all too sensitive to visualize that particular wavelength, or that to visualize the wave movement of that particle. So when I am moving, or when any kind of heavy particle is moving, a car is moving, a train is moving, so it appears to be moving in a straight line because the wavelength is very less, or we are not able to sense the wavelength. It's wobbling, but we are not able to sense its wavelength or sense its wave. Even Earth, it's a very hard mass, it's a very huge mass, so again the wavelength cannot be very high, so it appears to be moving in a small trajectory, or it's moving in a straight line, or moving in the straight circle. It's not going to show any kind of zigzag pattern. But for an electron, you can say the mass is too less. Obviously wavelength will be tremendously high. Now in this case we cannot neglect the wavelength of the electron, hence there is you can say the drawback of Bohr and De-Broglie can be concluded, and they can be mixed together. So now in this case, for an electron this cannot be neglected. So basically in electron it is not neglected, but in other particles like for us it can be neglected. So basically this is not for, in our theory it's not for any kind of particle, basically it's for electron. You get my point? So in every calculation the mass of the particle will be for mass of the electron, and you know what is the mass of electron? It's 9.1 into 10 raised to the power minus 31 kg. So every time we are talking about the mass of the electron, because in an atom you very well know what is the movable part, the electron, otherwise the nucleons are just stable, and we'll find the wavelength of that movement of electron only. Now just to confuse the examiner are very smart, so just to confuse you, this can also be written in the form of kinetic energies. So you very well know the kinetic energy of any particle can be expressed in the form of half mv square. Now I'm just making certain changes over here. If I write velocity, now according to this calculation, can be written as under root of 2 ke upon m. If I substitute this value of v in this De-Broglie's wavelength, my lambda will become h upon under root 2 times of kinetic energy into m. Now this is the most popular form seen till date in the exam. The question comes generally from this format, so you can learn the formula or you can derive it at that particular instant. It's not a big deal, you can just go with this. Fine. Now still I can very much assume that you are not going to be clear with the point that how it's like I have already studied in my earlier classes that it's not moving in the form of a wave, it's moving in a particular orbit, and all such theories were there. So I'll not agree. I can very well understand this thing. So I'll try to prove this part also with another point. Now the second doubt which comes in everyone's mind is when to use lambda for energy calculations and when to use that, like if they are asking me wavelength, when to use that is going to be De-Broglie's and when to use it's going to be energy. Now for you it's very easy. Generally whenever they want to find you the wavelength, and that is De-Broglie's wavelength, they will always try to specify. Like I have seen in majority of the questions they try to specify, whether it's in books or in exams, they specify that exactly they want De-Broglie's wavelength so that you don't get confused. But if supposing the examiner forgets, so what can be the trick? If something like kinetic energy is given to you, you can very well understand that the examiner wants you to find the De-Broglie's wavelength. Okay. Now coming to the next point, you are not satisfied with me or with the theories given how is an electron moving in the form of wave, not moving in the form of a proper circle pattern. And I can very well understand this conflict comes in your mind because since childhood you are being told that it's moving in the form of a proper circular path or a spherical path. Now this point again can be proved by one more thing, like if I say assume that it is moving in the form of a wave, obviously there will be some kind of waves or the number of waves made in covering that particular circle. So accordingly I can also find number of waves made by the electron in an orbit. Now this is just an extension of Bohr's theory. This point will also be proved by this. So if I move on, so what is Bohr's theory? Bohr's told us that an electron will not start moving at a random distance. It will be when your electrostatic force and the centripetal force are going to get equated, or in other words I can say the angular momentum of the electron becomes what? The multiples of nh upon 2 pi, you know it. So that means how does angular momentum represent? mvr is equal to nh upon 2 pi. Now I'm trying to mix these two theories so that it becomes much more clear. So now if I substitute this value of mv from De-Broglie's wavelength. So this can be written as h upon lambda into r is equal to nh upon 2 pi, or in other words I can say that 2 pi r is equal to n lambda. Now what is this expression telling me about? This expression is telling me about 2 pi r stands for the circumference of the circle and n lambda stands for the number of waves. N stands for, in this case, n stands for number of orbit you're talking about, or our concerned orbit. So obviously in this case, if I'm supposing this, what is the conclusion I can make from this particular expression which I am getting? And the conclusion is that, supposing if I'm talking about the first orbit, the number of waves required to complete first orbit will be 1, n lambda, in covering 2 pi r distance, that is the circumference of the orbit. Second orbit, to complete the circumference, it will make 2 waves. Third orbit, to complete the circumference, it will create 3 waves. And that was the reason whenever we are talking about, when you conclude the Bohr's theory, it's given there, it has got a failure, it has got a drawback that this will be used only for hydrogen-like species. The reason being is that the electron will not be moving in a perfect path, it will be moving in the form of a wave. So exact value of r cannot be calculated, you can very well understand. So from this only we can say number of waves made by an electron will be equal to the number of orbit I'm talking about. Okay, for example, I randomly show you, earlier you were told that supposing this is a nucleus, so this is going to be the trajectory, or this is going to be the path in which the electron is going to move. But now the latest developments tells us this is not going to be the trajectory of the movement of an electron. The electron will move like this, making a wave like this. So for example, I ask you for which orbit for which particular energy level I am talking about. So it's going to be, see, this part, you can say one wave, this part goes for another wave, then this completes third wave, then this completes the fourth wave, and this part completes the fifth wave. So there are 5 waves made in completing the full circumference of this orbit. That means that is just equivalent to that I am talking about which orbit? That is the 5th orbit. So that very well tells us that this theory is also very much applicable, and the electrons are not moving in the form of a perfect trajectory, it's moving in the form of wave, they are wobbling. Okay, so now this part was again utilized by another scientist, which we'll talk about in the later theory, that is the second part of this theory only. And let us start with some type of numericals regarding this particular topic.